Welcome back, Physics 30. This is the last part of Unit 1. It's Part F, Part 1, and Newton's Laws of Motion. It pertains to pages 115 to 125 of your duotang. And we'll look at free body diagram and unbalanced net forces, Newton's first law of motion, analyzing situations involving balanced and unbalanced forces on various objects with the aid of those free body diagrams as mentioned earlier. Recognize the importance of free body diagrams in analyzing problems in physics dealing with statics and dynamics, so things at rest and things moving in a specific direction due to a force. Transferring understanding of vector addition in one or more dimensions involving Newton's laws of motions. Solving problems involving Newton's law of motion and demonstrating understanding of the relationship between SI units of force and the corresponding fundamental units. So first of all, the first part of Unit 1 dealt with kinematics, the study of how objects move, so looking at the moving at a specific speed, velocity, etc., accelerating maybe. Dynamics looks at why objects move, so looking at the forces involved with them. So when studying forces, we look at Isaac Newton and the contributions that he made, specifically with the three laws of motion, but of course other things that he did. Invented calculus, also universal gravitation is another thing that he did. Newton's first law of motion. Objects at rest stay at rest. Objects in motion stay in motion unless an outside force acts on it, such as friction. So if first part of this makes sense, it's something's at rest, then it stays at rest. But if we push something and it starts to move, it'll stay moving forever unless some other force acts on it, and we usually see that happening because there's friction all around us. So that second part is kind of questionable, but once we realize that we have friction involved all the time, it makes sense. So objects in motion eventually stop in our real life because friction is that outside force that causes things to stop on Earth. So a force could be thought of as a push or a pull. 6 different effects of force on an object. If you look on page 120 of the duotang, you can look at different things there involving forces. I don't have it in front of me right now, but if you take a look there, those are the 6 effects that forces have on objects. And of course, force is a vector quantity because it has a bigness, it has a magnitude, and it also has a direction in which it acts on. The SI unit, or System International, or metric system used for force, is the Newton, named after Isaac Newton himself. Unbalanced forces, when you take all forces into account that are being exerted on an object, if there is a force in a particular direction that results, that's an unbalanced force. So it would be our resultant force, the overall force that acts on an object when all forces have been added together. And usually we have a variable to describe that. It's usually F net, or if we think back to our vectors unit, resultant, so FR, and of course we have the half arrow over top indicating that it is in fact a vector quantity. So 2 possible cases involving unbalanced forces. F net equals 0, so we could say that there is no unbalanced force. The object is at rest, so you could have 2 people pushing on an object in opposite directions and it would stay at 0, it's not moving. Or if that object had already been moving, and if we have 2 forces exerted in opposite directions, again F net would be 0, but it would be moving with constant velocity. That's a very important thing to note. Put 2 stars there because a lot of people don't realize that. Once an object is moving, and if all forces cancel out, that object will keep on moving with a constant velocity. Or we could have a scenario in which the net force is bigger than 0. That means there is an overall or resultant force on the object, so that object will be accelerating. Force leads to acceleration. So if we look on page 122, there's a bunch of examples, just simply drawing diagrams involving forces. So this first one, if I have something that's 35 newtons north, 48 newtons south, we can think of it like this. These are referred to as free body diagrams. They're just a way of visualizing what's going on. So just usually draw a box for the object and then the forces. So 35 newtons north, 48 newtons south, and of course you can see that 35 north will cancel with 35 south, leaving you with 13 newtons south. So it's very much vector addition. Moving north, then south, and then what is the resultant? This next one, 55 west, 34 newtons east. So we can visual like that, 55 in this direction, 34 in this direction. 34 cancels with 34, 55 subtract 34, and we get 21 newtons west. So relatively easy there. Just simply drawing out the diagram and then going from there. So here I kind of go into more detail about what a free body diagram is. Don't spend a lot of time drawing the object, just simply draw a box, that's good enough. If I have a scenario like this, 14 newtons north, 18 newtons south, 50 newtons west, 50 newtons east, it would look something similar to this. And you can see what's going to happen here. 15 west and 15 east, they'll cancel each other out. 14 north, 18 south, 14 will cancel with 14, leaving you with 4 newtons in the south direction. Okay, maybe pause the video now and see if you can sketch this next one and figure what the net force is there. There's F1, F2, this should be F3 and this should be F4 if that change hasn't been made on your booklet. So pause it and see if you can figure it out. Okay, if you had time to figure it out, 12 newtons west, 11 newtons north, 16 east, 11 south. So you can see the 11 north and 11 south cancel each other out. 16 north, 12 west, 12 cancels with 12, leaving me with 4 newtons in the east direction. Relatively straightforward. So free body diagrams, they're basically a picture. It helps to figure out what you're doing, gives you something to look at, and you can see all the forces involved when analyzing a problem. Okay? When there are more than 2 forces acting at different angles, so those ones are nice, they're north, east, south, west. What if we're looking at specific angles though? What we did with the vector unit is we break it down into components. So you should say physics rocks, by the way. So here I have a hanging sign. So here's a building here. There's a pole sticking out. The sign is just hanging from that pole. So of course we have a force pulling downwards, 2 forces pulling at 2 different angles. Those angles are 35 degrees and the forces are 174. So if we can break it down into vertical and horizontal components, the question becomes something like this. So that's what we have to do there. So of course we have SOHCAHTOA. So if we look here, determine the west and east components. So west and east, they're going to be the same value but opposite directions. So here we have our hypotenuse, our angle, Fx, the x component of the force, can be figured out by using cosine, of course. So cos of 35 equals adjacent over hypotenuse, and I get 143 newtons. So 143 newtons east, 143 newtons west. So as you can see there, that's what I have. To figure out the Fy components, there's actually 2 of them that are identical. Of course, the opposite side is sine. So sine of 35 degrees equals Fy over 174. Solving for Fy, I get 99.8. I just round it off to 100. And since I have 2 vertical components on this one and this one, I doubled that. So it's actually 200 newtons working in the northwards direction because there are 2 north force components. So if we look back here, the total north force is 200 newtons. These ones cancel out, so you can see what the downward force must be because this hanging sign is not moving. It's just hanging there, so That'll help you indicate what that is. So since sine is not accelerating up or down or sideways, the force up must equal the force down, so it must be 200 newtons downwards. Okay. One other force we're going to look at before we look at the vocab and bring this video to an end. It is the normal force. The force that an object exerts on another surface, or the force that the surface exerts on another object. For example, a book sitting on a table, gravity is pulling it down, the table is pushing it up. Those forces are equal and opposite, because otherwise the book would be accelerating downwards. Later on we'll look at it in an angle case, but we'll leave this for now and worry about that later. So a cup sitting on a table, Fg and Fn. Chair sitting on the floor, Fg and Fn. It's the same thing. So arrows should be the same length because they're the same magnitudes, just opposite directions. And of course, same thing here. So I just wrote ditto for that. The net force is 0, up and down forces cancel. Okay, so what we looked at, free body diagram, a diagram that illustrates all forces exerted on an object. Unbalanced force is the overall force applied on an object or the resultant. So we can see here in this case 5 and 5 cancel out, 7 and 10. I'm left with 3 newtons in the eastward direction when all is said and done. Okay, that's it. So that's the first force booklet on Newton's law of motion. See you soon.